test is going to be like a 40% class average. So bad.
Okay, so let's look at something here. Let's look at, I want to look at.
Did you put K in your answer or something like that?
What?
Did you put K in your answer?
Yeah.
He said not to.
I didn't. I had no idea what to do.
That's one of the ones you're having him grade though, or?
Yeah.
Okay, here's a function. Let's just call this f, right? Let's talk about what we know about how we can relate the characteristics of this function to calculus. Okay, so relate the first derivative to this function, just visually. Tell me what's going on with first derivative.
It's
Where's it zero?
the peak, so it's at like 0 and whatever that is.
Right there?
Yeah.
I'm going to get horizontal tangents, right? Okay, so if we were to look at this in terms of our table, right? And let's do that. Here's our table. So we got x, y. We don't care about y. Y prime. So what do we know? Whatever this value is here, and I guess we can infer that's probably 0, but we don't even care. If we just go down vertically, let's just call this point A, and let's call that point B. When x is A, what can you tell me that's important?
Y dot 0.
Ah, okay. And when x is B, y dot.
Or y prime.
Y prime.
Yeah.
Y prime is 0. Okay, and I guess we even have another one out here if we keep going. Let's call this one C. Same thing at C, right? So out here, I'll just scrunch it up a little bit. At C, we also get 0, right? Okay, so what else can you tell me about the first derivative in between?
Positive. Between A and B is positive.
Between A and B, it's positive. Because for our function, which is a smooth function, right? And we don't even have to say it's smooth, it's continuous, right? If it's continuous, then I know that the only critical numbers can occur at places where the derivative is either undefined or equal to 0. And we found them all, right? Those are the only places, right, where we got critical numbers. So those are the only candidates for peaks and valleys, and they all passed. They all worked, right? So then, is it possible that the derivative is going to change sign between A and B? No, it's not. Because to do that would require a critical number, wouldn't it? A peak or a valley. So then when I say that the derivative is positive there, that sums up the behavior of the first derivative the whole way. Agreed? Okay, what about here?
It's negative.
It's negative because it's decreasing, right? Okay, let's look at the next row. Ooh, what is the second derivative telling us? Now think what the first derivative is. You gotta really focus here. This is gonna hurt your brain. This is good. No pain, no gain. No pain, no brain gain. Like I said. Okay. So the derivative is the rate of change of the function, right? So we know that moving from left to right between here and here, as x increases, the function is increasing, right? The y value is increasing. That's why it's going up. Between this point and this point, as we move from left to right, as x increases, the y value is decreasing, which is why it has a negative slope.
It just kind of looks like a sine wave, though.
Okay, say it again.
So it just looks like a sine.
This one does,
Yeah.
right. Let's look at the second derivative. The second derivative is really just the rate of change of the first derivative, okay? So then, think what this is going to look like. If we start just right here, how about? At some point, let's just call this one Z. If we start at Z and move to the right, let's just look at the beginning here. I want you to tell me what's going on. What is the rate of change of the first derivative as we move to the right? As x increases, what's happening to the first derivative?
The derivative decreases until it gets to A where it's at 0.
The derivative does?
first or the second?
The first derivative, because the second derivative,
Yeah.
right, y double prime is really just the rate of change with respect to x of the first derivative, right?
Is it constant? Is it not constant?
No.
Is it
From Z to A?
Well, I don't know if it's
second
constant or not, but what I wanna know is what's the sign? Is it
No, it's
increasing or
negative.
decreasing?
For the first derivative?
Yeah.
Yes.
No, the second derivative. Is
So
the first derivative increasing or decreasing as we move from left to right, starting at point Z?
So it's, the first derivative, well, it'd be negative, you know that. But it keeps going, so would it be positive
Okay,
technically?
right, because we're not interested in the static value of the first derivative, right? That we know is gonna be, if I continued this, that would have been negative right there, right? What we
Maybe
want is the
positive.
rate of change.
Positive.
How come?
Because it goes all shoot, so it's like, so the first derivative, and then,
Good explanation.
the first derivative, it's so the graph, the initial graph has a negative thing right there, so that means the first derivative would be coming up from the bottom, which means that the second derivative would be positive, so it'd be coming up from the top.
Okay, but, okay,
Wouldn't it be just?
but let's not even look at it in terms of the graph of the second derivative function. You guys can do that. I know that we've done a little bit of that in the past, and we'll come back and review that. But I just want this in terms of just thinking about the rate of change of the slope. And let's maybe look at this in terms of what we might call a slope field. Let's just look at individual tangent lines that represent the slopes as we move along. What's happening from left to right to the values of those slopes?
They're decreasing.
What are they doing?
Getting closer to zero.
They're getting closer to zero initially, and then they're getting
Well, once we hit
bigger, right? But if it starts off at a negative value and then it moves to zero and then moves to positive values, what's it doing the whole time? It's getting more positive, isn't it? So they're getting more positive is another way of saying increasing, right? Does that make sense? The slopes are getting progressively more positive. Less negative means more positive, right? Agreed? Okay, so the rate of change of the second derivative down here is clearly positive, right? Okay, let's look up here. Let's look around this point, maybe like right there. Let's call that Y. What about there? What's happening?
So from like A to Y?
Yeah, from Y over to like B. What's happening to the slopes there?
Yeah, so it's decreasing.
They're decreasing. They're getting less positive and or more negative if I keep going, right? Does everybody agree? Okay.
So it's almost like relative streamer when only in that area?
Kind of. But let's see if we can define this. So it's positive here, right? Like let's take the point A. At the point A, the rate of change of the second derivative is clearly positive, isn't it? Right? Can you think of that in terms of the relationship between the curve and the tangent to the curve at A? So the second derivative here is definitely positive. Up here you told me that it's negative, so at B it's negative.
Wait, so if you were to go from Z, like from Z to B, would it just be no? Nothing?
Well, it's evidently going to somewhere change, isn't it?
Yeah.
Because it was positive at A and negative at B.
Is there any reason not to just graph the first derivative so it's like easy?
Yeah, there is, because I want you to be able to just look at a curve and be able to visually, and you're going to, in about 1 minute and 51 seconds, you're going to be able to tell me. That's what I predict. No, it's less. No, it's less.
It's about like 130 right
It's
now.
about 143 now. So what's the deal?
143.
What's the hallmark here? What's the relationship between a tangent to the curve and the curve in a place where the second derivative is positive? Where does the tangent sit? As opposed to a place where,
Oh, minimal.
well, okay, I mean, yeah, but it wouldn't even have to be minimum or maximum. I could do it like, right, let's pick, Let me pick a curvier curve so it's a little easier to see. Let's pick the value. I want to know right here. At that point, I want to know is this rate of change of the second derivative, or the first derivative, sorry, which is the second derivative, right? The rate of change of the first derivative, meaning the second derivative, positive or negative. Here's the tangent to the curve right there.
It's negative because it's because after it goes over the relative maximum, it's gonna start going negative. So
Okay, yeah, but I'm just looking at that one place right there. Okay, let's go back for a second. Think about this in terms of an ant. It helps. Think about ants sometimes. In a place where the second derivative is positive, right, where the rate of change of the first derivative is positive, if the ant is walking uphill, what does that mean is happening to the hill?
Approaching 0.
No, if he's walking uphill.
it's getting bigger.
It's getting steeper, isn't it? Right? The hill's getting steeper in front of him. The slope, the rate of change of the slope is positive because the slope is getting steeper. If the ant is walking downhill when that's happening, well, then the slope is diminishing. It's decreasing towards 0, right? Everybody agree? What about a place like up here where the ant is, or even right here, where an ant is walking uphill, but the rate of change of the first derivative, aka the second derivative, is negative. So the rate of change of the first derivative is negative. Doesn't that mean the slope is getting less steep? So now as he's walking uphill, it's tapering off, right? As he's walking downhill, that would mean it's getting steeper. It's getting more negative.
So
Right.
when it's more steeper, it's positive, but it's when less steeper, it's negative.
Well, if you're walking uphill and it's getting less steep, it's negative.
But
if
if
you're
you're walking
walking-
downhill and
It's getting more steep, then it's negative,
it's
right? Because it's getting more negative. But all you got to do is just compare where does the tangent line sit relative to the curve. If it's a place where the second derivative is positive, notice where that tangent line sits relative to the curve. Where? Well, it sits below the function, right? Below the function. Where it's the second derivative is negative, the tangent's going to sit on top of the function. So even in a place like this right here, is the function on top or below the tangent? It's on top, right? Isn't that curve on top of that?
Oh, okay.
Right, see what I'm saying? The curve sits on top of the tangent, and so that must mean it's a positive second derivative, right? What about at the point right, I don't know, right there? There's my tangent. Hard to see, but you can kind of get an idea that it sits, the curve sits below the tangent line there, doesn't it? So that's going to be a place where the second derivative is negative. So what we find out, we got a math word for this, it's called concavity, right? The second derivative corresponds to the concavity of the function. So over here, it is concave up where the second derivative is positive, which means that the tangents sit below the curve. It would mean that it would tend to catch water if water were falling on the curve, okay? Here's a place, or here's a place right there, where the value of the second derivative is negative, right? Because the tangent sits on top of the curve, or the curve would tend to shed water, right? Well, if this is positive and this is negative, what does that imply somewhere in between there must be? A zero, right? There's got to be a transition between positive and negative, which is the number 0. Where do you think that's going to be?
The moment that it switches from being up top.
Okay, so it's going to be where the concavity switches from concave up to concave down, and about there-ish, you think? So that's going to be the point maybe right there where the second derivative is 0. Okay, that's what we call, that's an important point. The place where we switch concavity is called an inflection point. Okay? Those are important though. Those are important points too, because a lot of times what we're going to do, like next chapter, actually this chapter, at the end of this chapter, we'll kind of go through the calculus part first and get good at that, and then we'll do a big application at the end, just like we did with related rates. Inflection points, like when you're talking about economics, this is oftentimes what we call the point of diminishing returns. So let's say that we're charting your profitability. Okay, if you're charting profit as a function of the amount of widgets that you're producing, right? So here's P, and then this is X is something that maybe it's the price of the widgets, maybe it's the, who knows. But whatever we're controlling and we're studying here, if the curve looks like this, then people oftentimes think, okay, well, we're going to aim for that point right there, because that's where profitability is maximized. A lot of times you don't. A lot of times you want to be really careful once you get past the inflection point, which is the point of diminishing returns, right? Reason for that being economically, that if you make a mistake here, you're going to be still going to be in positive territory. But if you make a mistake up here in the wrong direction, you can actually start to become less profitable, right? And so there's more to it than that. I mean, I've simplified that greatly, but this is a really important point for us in economics, right? Okay, so how could that be useful to us then? A couple ways. I mean, first of all, concavity is interesting in its own right. And so I'm going to ask you questions like, give me the intervals where the concavity of a function is positive and negative, right? And then you would have to work down in the second row. But what's really cool about this is all the work that we do, or the fourth row, I guess, all the work that you do in the second derivative row exactly mirrors everything you did in the first derivative row. So let's think about the relationship between concavity and inflection points in the second derivative as compared to relative extrema and the first derivative. You know, first derivative is just increasing, decreasing, it's slope, right? But how did we find the interesting places, the relative extrema? And for first derivative, the interesting places were extrema. For second derivative, they're going to be inflection points. How did we find relative extrema again? Okay, find where the derivative equals 0 or undefined, which we called critical numbers, right? All relative extrema have to exist at critical numbers, right? Okay. Not all of the critical numbers are going to produce relative extrema, but you can't have a relative extremum that doesn't occur at a critical number, right? That all makes sense? Where do you suppose that inflection points are going to live? At critical numbers of the second derivative. Not all second derivative critical numbers are going to produce inflection points, but all inflection points will necessarily live at second derivative critical numbers, right? So you're really getting a bunch of free, useful stuff in calculus, you know, really for no extra work, because it's the same process that you did before, only we just call the interesting places something different. And they show up as something different on a graph, right? Let's try this though, right? So if we want to find, let's see, what's a good example here? I just need to get like a forklift or something for my desk. All right, so let's do this guy. Okay. So we want to find the intervals on which this function is concave upward or downward. So concave upward, that corresponded to what sign of the second derivative?
Upward.
Positive.
Yeah.
Concave downward, it's an A. Negative second derivative. So all we got to do is the same kind of stuff we did before on our table, but we're just going to utilize that new row, right? So what's the first thing we got to do?
Find the derivative.
Find the derivative. Okay. So what do we get?
Wait, X. Oh, that's 2 now. X squared plus 3.
Okay, so that's going to equal, if we simplify that a little bit, that's going to give us what? Negative 12x over x squared plus 3 squared. Okay. What do we do next? Second derivative. What we really need is the second derivative, isn't it? So either we're going to use product rule here or quotient rule here. Let's just use quotient rule. Let's pull the negative 12 out front. How about? That'll make things a little bit easier. And then we just got the quotient of that. So what's that going to give us?
So
The bottom,
x squared plus 3
Times,
x
prime,
which is what?
1.
1 minus x times, what's the derivative of that?
2 x plus 3 times 2x.
Yeah, divided by,
bottom squared.
so to the fourth. Okay. All right, so let's clean that up a little bit. So then we just get, so we can, I'm gonna kind of make this, watch this closely. Here's a way you can abbreviate your notational work on this, right? So we could simultaneously factor out an x squared plus 3 and cancel it with 1 on the bottom, right? Everybody see that? So that's gonna make that a 1, that goes away, that becomes a 3, right? Everybody see that? Okay. And then that leaves us with negative 12 times this
Perfect.
exactly, times x squared plus 3 minus 2x times 2x is just minus 4x squared, good, all over x squared plus 3 cubed, right? Okay, which finally equals negative 12 times 3 minus 3x squared. Right? And it'd probably be useful to take a 3 out of there, too.
Sure.
So we end up with f double prime equals negative 36 times 1 minus x squared over x squared plus 3 cubed. That's all right. Okay, so now we got to find critical numbers. Is there going to be any place where the second derivative is undefined? And by the way, that gets a little bit tricky. I'm going to save that for another day, talk about that. About the critical points that are places where the second derivative is undefined. Okay. I'm not going to look at any examples of that today, just because it gets a little bit strange. Okay. But let's look at the kind where where the second derivative equals 0. Okay. So where's the second derivative going to equal 0? It's nowhere undefined, is it? How come?
Because you're not taking the even square root of a number or,
Okay.
or of an odd number or whatever. And there's something about not being on the bottom.
Okay, right,
You
so the
can't
bottom
do it.
can't be 0, but could we ever could the expression x squared plus 3 ever be anything except positive? No, right,
Well, if we got,
for real numbers.
Wait, are you sleep calculating?
Yeah.
I was, I think better that way.
Yeah.
It's osmosis, I believe.
Uh,
What if X was 1?
That's not how it's supposed
I gotta tell you a quick story about that.
Okay.
That's something came up. This is just like, my son, when he was a little bit younger, he's kind of a sleepwalker a little bit sometimes. And sometimes in the middle of the night, like when he was in grade school, if he was really tired, he would be, while he's sleeping, he would be doing things like going through his math facts while he was sleeping. Because you can hear him just saying, 5 times 7. I mean, he used to be totally asleep and he'd just be going through his math facts in his head. Anyway, proud parent. Yeah, proud parent.
Yeah.
Okay, so the bottom could never be, x squared plus 3 is always positive value, because the minimum value of x squared is 0, right? Okay, it's all, x squared by itself is always non-negative.
Okay, but what if we plugged in 1 point, nope, never mind.
Okay, so then let's look at this again. So then if we're looking for critical numbers, f double prime, now remember this is what I like you guys to do. We'll say f double prime equals 0 when what's true? What's the only part of the top we really have to focus on? Yeah, it's this part right there, right? Right? That's a constant. That's never going to change sign. But this could be 0. So it's going to be when 1 minus x squared equals 0, which is when x squared equals 1, which is when x equals what? Plus or minus 1.
Is that a
So
36 on the top? Sorry.
36, yeah, that's 36.
3G.
Okay, so those are my 2 critical numbers, right? Okay, so all we got to do then in our table, wow, that takes a lot of space.
Yeah, my notebook's almost full.
When you wake up from a calculus high.
That's a lot of space, yeah. Okay,
It's a
so
lot
we'll
of
just do this. Let me,
Work.
you know, I used to have in my past life when I taught in McMinnville, I taught calculus and physics and stuff. I had them installed for Promethean boards. I had whiteboards just all the way around, so I could just like start over there and just start writing and just go all the way around.
That's sick.
It was it was great.
That'd be awesome.
I wanna see that happen.
That'd be awesome.
Just taste the room
That'd be
as you
way
talk.
cooler than
Wait, so those like pictures of just like 5 chalkboards, just like with just chock full of math, no pun intended. Actually, did. But that's realistic.
Oh,
Yeah.
please come.
Oh,
I wanna see that. Like,
I wanna see the
what would you
logic
have to,
behind that.
what would you have to do to make something that large? Like, what kind of equations would come
What
up?
kind of ungodly person would make some?
I had a quantum mechanics problem set. My weekly quantum mechanics problem set once in college was 4 problems, and it took me over 100 pages of math to do those 4 problems. It was just
Those poor
pages
trees.
and pages and
What were you trying to
pages
figure
and
out?
pages. Oh, it was actually we were proving some, you know, we were like deriving states of a simplified atom.
The teacher just looks at
It
it.
was, but it was
Well, that's 100 pages. Perfect. 100
no,
pages.
I mean it was, you know, it's not like it was just dense math on every page. There were some diagrams and things, but it was. I mean, I think I saved it somewhere. It's just a
Can you bring it
ridiculous
into
problem set. Yeah.
How does the
Find it.
teacher grade it? Like, how much
Yeah.
time does it take to
They
grade
don't.
that?
The
Partial
TAs
credit.
graded it.
Partial
The TA's
credit.
crazy. Yeah.
Okay, so I mean I don't remember what the exact number of pages was. I can't remember. Maybe it wasn't. Maybe it was 79. But I want to say it was
Too
like
many.
it was a lot. I mean, it was
More
a
than
lot.
10.
It was a
It's
lot.
like a pot assignment, or you know.
It was really large. So anyway, so let's look at this here. So let's make our table, right? So we've got
I was actually drinking and I used my calculator. No, I actually wasn't. I looked up. No, it's not there.
That's sad.
I didn't even in this case really need to put rows 2 and 3. They don't do anything for
No,
us.
nobody
Right?
cares.
I did, but we don't need to. Our critical numbers are at -1 and 1. And if we go back and look at our function, no domain was prescribed for us. So what is the domain here? Are there any restrictions on our function?
All reals.
All reals. Yeah.
17.
Right? These were zeros of the second derivative. So what do I do to figure out the intervals on which the second derivative is positive and negative?
Plug in a number between.
Test points. So 0. So let's evaluate what's the sign of f double prime of 0. Well, that's gonna give us negative times positive, right?
Yeah.
Divided by positive is what?
Negative.
Negative. So let's try 10. If I plug in 10, sometimes I like to use values, sometimes they're just obvious, right? Doesn't make, I could use a billion if I wanted to. I just need a point between 1 and infinity, right? So if I put in 10, I'm gonna get negative times negative over positive is positive. If I put in negative 10, you get the same thing, aren't I? Because the only x's in here are x squares, right? So do you see that when that's true, when all the powers of x are even, the function is insensitive to the sign of x, right? So what's my answer? On what open interval or intervals is this function concave up? A negative figity to what?
Negative what?
To negative 1.
To negative 1, or
1
1
to
to
infinity.
good,
Beyond.
and it's concave down on
Negative
Wouldn't
1.
it be
1.
good.
Wouldn't it be and though, not or?
No, it's or, because you can't be both simultaneously.
Psych.
An ant can't simultaneously fulfill both of those criteria.
It's like once you get to that point where you have like the two lengths of this way where you can no longer stand.
The ant either has to be standing over there or over there.
But isn't that saying that it can only be concave on this one or this one?
Yeah.
Exactly.
It's a graph.
No, it's,
What?
oh, I see what you're saying. Where is it concave? No, this is, but the concave, the function, the second derivative is positive when x is less than negative 1 or greater than 1. Second derivative is greater than. See what I'm saying?
Oh, yeah.
Okay.
Maybe.
And then this is an
I
and
think so.
statement. The second derivative is negative, so it's concave down when x is greater than negative 1 and less than 1. Has to, it's bounded on both ends, right? Okay. So, what do you think about then? I really want to get through this. Am I gonna have time?
No.
Yes, I am.
2
You have 2
minutes.
minutes.
2 minutes.
Oh.
Not enough time.
Oh, darn.
Rats. That's at least a 3-minute problem.
We know when lunch starts, I mean, come on.
I think it's snowing out there. I think we should get an early start.